Students, now my intention about this topic is to make concept clear about electronic configuration. Expected learning outcome from this discussion is you should clearly understand how electrons are filled in various orbitals. Are there exceptions? If they are, why? Are there any complications while understanding the electronic configuration? Those things we will discuss in detail of electronic configuration. I could have teach this topic as is in the book, ideal configuration, observed configuration, but I want that before going to that you should know what is the electronic configuration. Students, right from your 8th standard in chemistry, you are studying electronic configuration, electron filling. At the beginning, K shell, L shell, M shell, N shell, 2 electron, 8 electron, 18 electron. Likewise, the concepts were taught to you. Afterwards, you might have come across 4 quantum numbers. Which are those? Principal quantum number means it says a shell number, orbital or azimuthal quantum number means it informs about the orbital. Third, magnetic quantum number, suborbitals means if p orbitals are there, why only 3 p orbitals are there? If d orbitals are there, why 5 d orbitals are there? F orbitals, why 7 f orbitals are there? That answers we can get from the magnetic quantum number. And last, that's the intrinsic quantum number, that's a spin quantum number. And we understand it is a clockwise or anti-clockwise in that say. It is for our understanding purpose we were following, and because of it only electronic configuration becomes difficult for us. I make you the concept clear. Up to atomic number 20, there is a no question Booth's principle is clearly followed. 1s orbital, then 2s orbital, then 2p orbital, then yes 3s orbital, then 3p orbital, then 3d should be there, but 4s comes over there, and their order only given as a 4s first and then what, the 3d. If it is so, 4s orbital is filled first, then for chromium, why only 1 electron in the 4s orbital? In copper, why there is only 1 electron in the 4s orbital? What answers we were giving till now? Chromium, by putting 1 electron in the 4s orbital, can accommodate 5 electrons in 3d orbital, and 5 means half filled orbital, and it governs some extra stability. Same dialogue we put for the copper, only in spite of half filled we say completely filled d orbital. Now I take this logic only. If half filled orbitals are stable, then why only for chromium? It could occur at vanadium only. Keep 0 electron in 4s orbital and 5 electron in d orbital. Why not 5 electron goes in the vanadium? Are you getting this point? Same thing. At copper we are seeing 3d10 configuration. Then why not at nickel occur 3d10 configuration? Means our logic, whenever we want, we are applying. And you were also accepting that. That was our till now train. Okay, I understand. It was a train. But as we go to the higher elements and their electronic configuration, a concept becomes somewhat tough. Students, in this periodic table, chromium is represented in group number 6. What is its electronic configuration? Outermost electronic configuration 3d5 4s1. Below chromium there is molybdenum, atomic number 42. So what is expected electronic configuration for molybdenum? 4d5 5s1. Right. Accordingly, the element with atomic number 74, tungsten, represented by W, wolfram. What may be the electronic configuration? 5d5 6s1. Now let us see whether what we discuss now, same electronic configuration, is there or not. Right. For chromium, what we were expecting, same electronic configuration is there, 3d5 and 4s1. For molybdenum also, as per our expectation, electronic configuration is 4d5 5s1. But for tungsten, 5d5 6s1, that was expected configuration in accordance to the chromium and molybdenum is not there. Then where is our rule that completely half field governs extra stability? So what exactly may be there, that we are going to learn. So don't be influenced by the previous general chemistry statement. Now we need to go somewhat deep to understand the electronic configuration. Students, I like to explain anomalous electronic configuration by one more example. Now just pay attention towards group number 10. Which element is there in group number 10? First element, nickel, with atomic number 28. What is expected electronic configuration for nickel? 3d8 4s2. Then the element below nickel, that's a palladium, atomic number 46, 4d8 5s2. And for platinum, 5d8 6s2. Let us see whatever we expect, is it proper or not. See here, for nickel, two possible electronic configurations are there. One, as usual, 3d8 4s2, and other 3d9 4s1. Then how can we explain 3d9 configuration? Because it is not completely filled d orbital configuration. Okay, let us see the other element. Now this is palladium below nickel. And no of the electronic configuration of nickel is represented here. What is represented? 4d10. There is no electron in the 5s orbital. It is very different than that of the nickel, though it is below nickel. Now for next element below palladium, platinum. What we are finding here? 9 electrons in 5d orbital and 1 electron in 6s orbital. It is different than palladium, but is somewhat similar to that of the nickel. So it is not very certain that always completely half-filled orbital will be the attempt, or only to fill the d orbital or half fill the d orbital, electron from s orbital will shift to d orbital. I want to emphasize that. Therefore, I had given you these examples. The problem that arises is due to our generalization of idea of electronic configuration. We are measuring all the atoms through one scale only. We expect whatever our rules are there, those should be followed by each and every element. We are not understanding the reality within the atom about the energetics of orbitals. Without that, we are expecting. Up to few level, up to few atomic number, our generalization principles were strictly followed. It doesn't mean those will be followed for others. Now question arises, what is exactly, what are the actual principles or what are the actual ideas for the electronic configuration? Before that, we should understand what are our general things or generalization principles that we think. See here, out of our one of the principle, Hund's rule of maximum multiplicity. What is represented there in first diagram? Three electrons are there in 2p orbitals and each electron is in separate orbital. And in second diagram, two electrons in one orbital, one electron in one orbital and no electron in third orbital. Which is correct one? First one is correct one. So electronic configuration will try to occupy the various orbitals as far as possible, as far as there will be the maximum multiplicity. It is called as Hund's rule of maximum multiplicity. Fine. Now, it is a Paulis exclusion principle. What it says, no two electron in an atom will exhibit all four quantum numbers the same. Means pairing of electron concept came in the same suborbital. Means in 2s orbital, if I have to fill the electron, two electrons, then both electron will not carry the same spin. Unlike spin will be there. About this Hund's law of maximum multiplicity and Pauli's exclusion principle, there is a no more question. Main concern is about the next rule which we generalize popularly and due to which we are in the mess about the electronic configuration. What is that concept? How to overcome the difficulty, that we will discuss one by one. This is a diagram for Bohr principle. What it says, electron filling takes place from low energy orbital to high energy orbital, and arrangements of orbitals in increasing order of energy is represented in this diagram. Means after 1s orbital, 2s, 2p, 3s, 3p, then 4s comes. After that 3d, 4p, 5s. In that way we can understand the sequence. It is in this diagram that 4s orbitals are of lower energy compared to 3d orbitals. Therefore, after argon 3p6, at potassium 4s orbitals start to fill. Then at calcium also 4s orbital. Then from scandium, atomic number 21, 3d orbital starts to fill. It is our understanding about the Bohr principle. This is the idea from general chemistry. It is a generalization of the electronic configuration. Now, it is a need for us to go deep or in reality understand the energetics of orbitals. We need to understand penetration ability of the orbital, shielding effect for an electron, then concepts of energetics of orbitals will be clear. Let us try to understand this energetics. Now see this diagram. It represents radial distribution for various orbitals. Radial electron density is on y-axis and distance from the nucleus is on x-axis. See the first orbital, that's a 1s orbital. You find a maxima immediately near to the nucleus, and that orbital nearly ends at 2 angstrom unit, or you can say 3 angstrom unit. Therefore, I can say 1s orbital, which is represented by blue line, is innermost orbital. Now come to the second orbital, which is represented by red line, that is 2s orbital. It starts from the nucleus where probability of finding electron is 0. But after nucleus, little probability of finding electron in 2s orbital is there. And near about 3 angstrom in it, there is a maximum probability of finding the electron in 2s orbital. And that story continues till 6.6 or near about that angstrom in it. There 2s orbital completes. If you see the third orbital, that is 2p orbital, at nucleus there is no chance of finding the electron, but near about 2 angstrom unit, there is a maximum chance of finding the electron in 2p orbital. Slowly its probability of finding electron decreases, and at 6.2 it becomes 0. So from this diagram, what do you think? Which orbital has a large spread? Which orbital can reach up to the large distance, far distance from the nucleus? 2s orbital or 2p orbital? Yes, the diagram says 2s orbital has larger jurisdiction from radius point of view compared to 2p orbital. So as per this diagram, which orbital should be there first? 2p orbital. Afterwards, next orbital should be 2s orbital. Is it our conventional way of understanding the arrangement of the orbitals? No. Till now what we have learned, 2s orbital comes first and then 2p orbital. So we are talking about energetics of the orbital, not position. About energetics only concern is there. Energetic point of view, 2s orbital is of low energy compared to p orbital. Again question you will be with, if electron is away from the nucleus, if distance is more, then how will its energy be lower? It is against Bohr's theory. It is against our understanding of lower energy of the orbital. Yes, student, absolutely, you are right. If distance increases, energy also should increase. But if you pay proper attention towards the diagram, 2s orbital has one node, or near nucleus 2s orbital has one maxima, and due to that maximum, nucleus is near to the electron, or more correctly, electron spends some time towards the nucleus. On an average, if you see, 2s orbital electron is closer to the nucleus. 2s orbital electron spends more time towards the nucleus. If it is a closer, its energy will be lower. And that closeness of the orbital we understand by the term penetration. 2s orbital is more penetrating than 2p orbital. Therefore, its energy is lower. Therefore, conventionally, traditionally, or in general chemistry, we represent 2s orbital first and then 2p orbital. Are you following what I am saying? Now see in this diagram, to avoid confusion, I represented 1s orbital, 3d orbital and 4s orbital. By blue line, 1s orbital is represented. It clearly reveals that it is very close to the nucleus. Probability of finding electron in 1s orbital is near the nucleus. Now our main point is 3d and 4s orbital understanding. From this diagram, what you find, which orbital has more spread, which is away from the nucleus? Yes, 4s orbital has more spread compared to 3d. So as per this diagram, 4s orbital should be of higher energy compared to the 3d orbital, keeping in mind spread point, keeping in mind distance of the electron from the nucleus. But that is not the only way by which we have to understand the energetics. We need to understand probability of finding the electron in the 4s. This 4s orbital has 3 nodes, and in red dotted circle it is represented. Near nucleus also its chances are there to spend time. So most of the time 4s electron spends near to the nucleus compared to 3d. So though 3d orbital's spread is less, 4s orbital is of lower energy. Which term we use for that closeness? Yes, penetration. 4s orbital is more penetrating than 3d orbital, therefore its energy is lower. Yes, means if you have to fill the electrons, you will prefer first 4s orbital. After filling that 4s orbital, we can allow the enter to enter in the 3d orbital. So which orbital has higher energy? 3d orbital has higher energy. Now I ask the question to you, if you want to remove the electron, then which electron will you remove first? Electron from 4s orbital or electron from 3d orbital? At that time you say electron from 4s orbital. Actually electron in 4s orbital has a less energy. Then how can you remove it first? First higher energy electron should go, no? There we do not understand the actual electronic configuration concept. See, metal atom or any atom, its electronic configuration is a one system. Its ion is a other system. And in that system, whatever the energetics is there, accordingly electronic configuration will be there. Since energies of 4s and 3d are comparable, are nearby, actually we find as if like electron from 4s electrons are going. What is there actually? Electrons are going. Afterwards, whatever the ion and its electrons are in, whatever the electrons in ion are there, those are arranged in various orbitals. And we find there is a no electron in the 4s orbital. Therefore, we say electron from 4s are removed. It is not likewise. This will be more clear when we will discuss the oxidation states of the lanthanoids. But let us understand first the electronic configuration of the lanthanoid. So what is the conclusion? Penetration of the orbital decreases the energy for that orbital. If it is so, then all s orbitals should be of low energy. Is what I want to say.
3s orbital is more penetrating. 4s orbital also is more penetrating. 5s orbital also is more penetrating compared to the other orbitals. But there is a limitation. After all, spread also increases. So combination of penetration ability and shielding effect or shielding phenomenon executed by inner electrons on outer electrons in case of the nuclear force of interaction, in case of attraction towards the nucleus. Combination of all those decides the actual energy of the system. Energetics in metallic state, energetics in atomic state, and energetics in ionic state for the same element I am saying may be different. Energy levels will vary, electronic configuration will vary. In case of transition series elements, when any ion forms at that time, effective nuclear charge increases and it affects d orbitals more than the other orbitals. Therefore, electrons we feel as if like are going from the 4s orbital because whatever electrons are there, those are entering in the d orbitals. So students, let us discuss actual electronic configurations of lanthanoids in next part.